Hello everyone, I am Vamshi from EC department. My AIT Tech Talk topic is about FPGA for 5G communication. Abstract. Next generation communication re- relies on standardized protocols, heterogeneous architectures, and advanced technologies that are envisioned to bring ubiquitous and seamless connectivity. This evaluation of communication will not only improve the performance of the existing networks but will also enable various applications in other fields. While integrating different heterogeneous systems, this massive scaling of mobile communication requires higher bandwidth to operate. 5G promises a robust solution by offering ultra low latency and high bandwidth for data transmission to provide individuals and companies with a real time, social, and all connected experiences. An end to end coordinated architecture which is agile and intelligent has to be designed at each stage. As FPGA has the potential to be resource power efficient, it can be used for building up constituents of 5G infrastructure. It can accelerate network performance without making a large investment in new hardware. Dynamic reconfigurability and in-field programming features of FPGAs compared to fixed functions ASICs helps in developing better wireless systems. This article presents various applications areas of FPGAs for the upcoming 5G network planning. Introduction. The next generation of communication is beyond present day internet and is moving toward the internet of everything. IoE. 5G, a key pioneer in this, will unleash an ecosystem for connecting billions of devices with optimal trade-off latency, cost, and greater capacity. Highlights certain salient features of 5G. It is estimated that around 50 billion devices will be connected to 5G network by 2020. So the network must be able to cope up with diversified demands compared compared to today's 4G and 4.5G LTE advanced, which is about speed improvement. The evolution of 5G focus on connecting new IoT and critical communication use cases which require several performance enhancements. IoT connections are characterized based on the volume of connection, data traffic, and energy consumption for certain applications such as self-driving cars, health services, and so on. Ultra low latency communications is a requirement, while for some other applications devices operating on low power mode is a requirement, helping them to operate for longer durations without regular maintenance. On the other hand, there are several cloud-based applications for data analytics that are require higher bandwidth and speed enhancement according to the International Telecommunication Union. 5G network services can be categorized as enhanced mobile broadband, ultra reliable and low latency communication, and massive mission type communications. EMBB focuses on services which require higher bandwidth, such as high definition video streaming, virtual reality, augmented reality, and web browsing. URLLC aims at providing services to latency sensitive devices used in applications such as industrial automation, autonomous driving, remote surgery, and remote management. MMTC aims to meet the demands of the digital society where the connection density is high, such as that for a smart city. As shown in figure 1b, 5G is about distributed network architecture in which data from the core network is transmitted to the macro base stations through radio network controller RNC. 5G macro cells use massive MIMO antennas which benefit a number of users to connect simultaneously to the base network and provide higher throughput as compared to the macro network, which has a wide coverage area. Small cells can be used for shorter range operating in dense environments. Small cells operate in the mm wave frequency range and provide increased data capacity which improves the performance to the connected devices. Technical challenges in 5G. Infrastructure developing a new type of communication system depends on globally accepted standards, which ensures interoperability and affordable costs for deployment of the system. Some technical challenges for meeting the demands of a 5G network, which are follows: medium access control. In the case of dense deployment of access point and user terminals, throughput of the system will reduce and latency would be high. So there must be a proper protocol algorithm for handling massive number of connected devices without affecting their performances. Data traffic management. Moving from traditional communication towards deploying machine to machine communication will not only overload and congest the network but will also pose a threat to the radio access network. Multi-service network. 5G has to offer diversified services to heterogeneous networks and services operating in different geographies. These devices may have varied specifications, that is, a few might demand low latency, some may demand high bandwidth. So, the transport network has to be intelligent enough to provide dynamic, user centric, and data rich wireless services to various and devices satisfying their specific need. Power consumption. Reducing energy consumption for the services provided is specific to help end user equipment have better battery life, communication, navigation, and sensing. These services are highly dependent upon the radio spectrum allocated, as the transmission capacity depends on that. The vision of 5G is strongly relying upon the hardware infrastructure. Hardware design should be confident FPGAs with the characteristics of dynamic partial reconfigurability and the ability to perform at higher frequencies make it convenient for designing various building blocks of the 5G architecture. Also, FPGAs have excellent advantages like hot real-time processing, which helps in radio signal processing parallelism, which helps multiple kernel computations in the same FPGA, and energy efficiency in case of fixed precision computation, that GPUs. However, there are a few challenges associated with the use of FPGA based system designed for CRAN. Radio access network is designed to communicate between base stations and end users. CRAN is a novel architecture meant for centralized and cloud based processing, where the baseband unit is relocated to a centralized pool called the BBU pool. It enables collaborative radio network, real-time workload virtualization, and large-scale deployment. These BBU pools are connected to the network stations through high-speed optical fiber and maximize the distance between macro to small cells. The CRAN architecture can be perceived as a cloud computing environment where the baseband and channel processing is virtualized and shared among the operators in the baseband pool, which leads to better traffic handling and maximum utilization of resources. It is built on interfacing card and hardware, which creates links between base stations and the optical fiber network. Apart from easier deployability and scalability, the cost effectiveness and the manageable solution towards a huge user base will make it a reliable infrastructure component for 5G. The figure shows centralized RAN architecture. The BBU pool. The BBU pool is located at a centralized site functioning as a data center. It holds a number of baseband nodes which are capable of performing complex computations and storing huge data. It has the ability to dynamically interconnect within the nodes or work individually as per the network needs. The communication among the units happens on a larger bandwidth and a lower latency. After processing, it allocates resources to the RRUs as per the network demand. RRU network. It is a traditional wireless network which converts wireless devices to the access point. Transparent network. It is also called the frontal network. It is communication layer between the BBU and RRU, which provides a higher bandwidth channel for handling multiple RRU networks. It can be optical fiber based linking capable of transferring high bandwidth with a faster rate, but it adds more cost. On the other hand, we can have cellular communications at an wave level, which is much cheaper than optical fiber. There are various challenges in deploying CRAN architecture. Some of those with possible solutions are listed below. Corporation BBUs. The BBUs in the same pool should cooperate with each other to share the computing data and should schedule them as per user requirement. But such cooperation is not defined and that introduces challenges in ensuring low latency, high bandwidth communication among the BBUs, and also affects the user privacy. FPGA based solution. High performance logic in FPGA can be used to reduce latency of interfacing among the based units. At high capacity stations, integrated block RAM can be used for switching among the BBUs. FPGA based solutions. The ability of FPGA to modify its operation at runtime with the partition safe mode enables it as a shared compute resources in CRAN. FPGAs can run multiple applications by virtualizing compute resources and also offers protecting through isolation of applications from each other. Multi-connectivity. As the dual connectivity feature in LTE helps devices access base stations on different frequencies. Similarly, multi-network connectivity in 5G over multi-mode base stations such as GSM, LTE, UMTS and Wi-Fi enhances peaks throughput of the devices. However, deploying on a multi-mode base station increased with capital cost. Cognitive radio framework for 5G. The potential increase in the number of users in a mobile network and the requirement of high data rate pushes 5G to work within a mixed ecosystem of micro and macro cells. Further, the stand-alone base stations will be replaced by a centralized systems as per availability of a high bandwidth backhaul network. So an adequate amount of spectrum allocation is required to be performed efficiently. The radio frequency spectrum is a part of nature, so the licensing and regulation of the spectrum is handled by the government. However, fixed spectrum allocation by government bodies leads to underutilization of resources when a certain spectrum range is idle. So assessing this underutilized spectrum is a challenging problem. Then the spectrum scarcity itself, since failing to utilize existing spectrum. Here cognitive radio has the ability to identify the underutilization of the spectrum. Applications of FPGA in 5G. 5G is the origin of integrating IoT machine-to-machine and machine-to-human communications along with the current communication technologies on top of newer network infrastructure such as cloud-based radio access network, software-defined network and the network function virtualization and so on. The ability of the FPGA to reconfigure itself dynamically enables us to change data transmission capacity along with the switching between services as per the current requirement. All these abilities of FPGA are pushing leading FPGA manufacturers to invest more to make their hardware more capable of dealing with the growing communication technologies. As FPGAs are performing well in signal processing, giving faster output and higher throughput, they can be used for signal filtering with telecommunication.